Hi, you're looking at a photomicrograph of an igneous rock. We can see the randomly oriented interlocking crystals characteristic of an igneous rock. If you remember the work we did in year 12 on identifying key minerals using a geological microscope, you'll be able to recognize the black and white distinctive sort of stripy pattern of plagioclase feldspar, the sort of yellow colours of augite, and then the really vivid colours with the heavy fracturing running through them of olivine. This clearly is some type of mafic igneous rock. But with this topic, I want to go beyond just what this rock is. And I want us to start considering the question of why is this rock like it is? What is it that makes igneous rocks so characteristic and so different from each other? Now, I've called this topic magma forming processes. Perhaps really what I should be described it as is magma evolution processes. And what I want to do with this video is just introduce some of the key ideas we're going to be covering as part of this topic. I want us to think about the ways in which magma will actually change and the influence that has on the igneous rock that's produced. What actually happens then as the magma goes from being a liquid into being a solid. Okay. A lot of what we're going to look at is based on the work of these two geologists. We have, in a rather nutty waistcoat there, Norman Bowen, and his research partner, Orville Tuttle. Now, these two geologists were working on the experimental reconstruction of crystallization processes. And the result of this experimentation is a really important idea in understanding igneous rocks. It's an idea we call Bowens reaction series. Now, there's a separate homework activity based on Bowens that will explain this series in some detail. So I'm not going to get into that at the moment. But if we're to summarize Bowens, really in one sentence, it's that we see an ordered progression of the crystallization of different minerals. It doesn't happen at random. Different minerals crystallize at different temperatures. And we'll see that reflected in the rocks that we find. Now, this has a number of different effects. The first of these is called fractional crystallization. You may have heard in science of ideas like fractional distillation, where we can distill different liquids at different temperatures. Oil processing, oil refining is an example of that. Fractional crystallization is looking at the crystallization of different minerals at these different temperatures. So we'll have some minerals that crystallize very early in the cooling of a magma. Olivine, for example, crystallizes at very high temperatures, so it's one of the first minerals to crystallize. Now, if that happens, what we can see is those crystals that form, which can be denser than the magma that they form from, then will sink through the magma. The result of that is we can get accumulations of particular minerals at the base of intrusions. And that can be also one way that we concentrate valuable minerals. More of that in a later topic. We'll see, as a result, these sort of distinctive layers. This rock, for example, looks sedimentary. It is in fact igneous. We've got concentrations of these minerals forming in layers at the bottom of igneous intrusions. There are some very famous examples of these. We're going to look at several of them through the course, two of them in this topic. We're going to look at the Palisades Sill, New Jersey in America, and we'll also look at, slightly later on, an intrusion in Greenland called Skaregard. And when we get on to look at the geology of natural resources, we'll look at an example in South Africa. But the Palisades Sill is an enormous intrusion. It's extremely thick, 250, 300 meters thick in places. And because it's so thick, we see some very distinctive layers within it. This is going to be a topic of a whole lesson slightly later on in the topic. So Bowens reaction series is crucial in understanding how these fairly major structures actually form. But we can also look at this on a minor scale. Here we see some more photomicrographs, this time of individual crystals. You can see within these crystals then different zones. These zones can be of different chemical compositions. We can actually see the evolution of the magma that's forming these crystals preserved within the one crystal. This is a topic of another homework task that you're going to be working on. So again, I'll leave that explanation for another time. So far, we've looked at these crystallization processes that, if you like, are taking material out of the magma. As an olivine crystal cools, crystallizes and sinks to the bottom, the magma is taken out of the mix. We can also see changes because of material coming into the magma. This, for example, this is an example of Shap granite, which is going to be the topic for another lesson that we're going to be coming up on fairly shortly. You can see within this specimen this dark lump. Now this dark lump is either perhaps a xenolith, or it might be a feature we call an enclave. Either way, this is material that's being put into that magma. It could be a blob of more mafic magma being injected into the silicic magma, or it could be a lump of country rock falling into the magma, which then partially melts, putting more silica into the magma. Either way, the composition of the magma, the properties of that magma, are going to change as a result. It does perhaps contribute to our understanding of what's actually happened in the formation of this rock. You can see perhaps some of the effects of this in this quite spectacular xenolith found in the Ardrog granite in Donegal. If we look at that close up, we can see how the properties of this xenolith must have made it liquid, or certainly very, very plasticky. We can see there the intrusion of little veins of granite into the more mafic material. This is starting to combine. There must be an input of new mineral material into that magma. Now this is all related to the process of stoping. Now this was part of our Year 12 course. We know that this magma moves upwards because it's buoyant, it's under pressure from the gas, forces its way through weaknesses, but it changes the magma because some of the minerals in that country rock are going to be melted into the magma. And that process is going to be selective. It's not all the minerals that will melt, it's going to be the ones with the lower melting temperatures that will melt and become incorporated into the magma. That inevitably makes magma more silicic because it's the more silicic minerals that melt at lower temperatures. Bowens reaction series tells us that. So, to conclude, magma changes in a number of different ways, either by elements being taken out of the magma mix or new elements being put in as they're incorporated from the surrounding rock. Either way, that has an effect on both the rocks that we see and some of the other wider igneous processes that occur as a result. Volcanic activity, for example. We're going to explore these ideas in more detail in individual lessons. Our first step, though, is to understand more about, firstly, Bowens reaction series and also the role of xenoliths and enclaves. Those are our next lessons, and then we'll start looking at some of these places we've been talking about in a lot more detail. I'll see you then.